Jericho, can you also make me co-host so I can record it on my computer and then it is easy to upload it?
Right, of course. About, well, yeah. Make a co-host. So you co-host.
Okay, thanks.
So we want to show that if you are in that theory, working in the model of that theory, then doing this, just adding one coin subset to theta, which is omega 2. Satisfies CH plus there is an omega 1 dense ideal. So we get a little bit stronger thingy. We will get a stronger conclusion. We will get, so we get that the, so we get I such that 1 if G P omega 1 I is generic, then the generic embedding restricted to the ordinals is actually the embedding by the Solovay measure restricted to ordinals. Mu is the Solovay measure. Solovay measure on omega 1R, and 2 we get, this is consequence of density, so we also get that G omega 1 is actually omega 2, but that's because it's omega 1 dense, and so CH omega 1 dense, that would imply that omega 2 is not collapsed, whereas omega 1 is collapsed. So this just already follows. But 1 is a stronger condition. Usually you have, what does it say? It says that the embedding, generic embedding, is independent of the generic you pick. It's always this thing on ordinals. So you would get such a thing if you were collapsing like a large cardinal, for example, right? So if you derive ideals the way you, in the traditional sense way, right? In the traditional way, you will collapse a measurable to omega 1 and then try to leave the embedding. And then you would have that it doesn't depend on the generic. The embedding restricted to the ordinals does not depend on the embedding because it's always the one that comes from V, yeah, that comes from the ultra power. So this is what it is. Okay, all right, so what did we prove so far? So far we, I guess the key lemma is, I'm not going to stay because we don't really need it anymore, but we will need the following definition. So to show this one, we will need the following definition. I'm not sure how important 1 is anymore. So maybe I don't concentrate on 1 that much, but let me just tell you. The reason 1 was important before is because, okay, so it's important for philosophical reasons, because you get from, if you were able to force this thing from large cardinals via traditional ways, then you would get something like that. But there was also a technical use for it in the Kolmar induction arguments. So this reversing this, the two theories are actually equivalent, equiconsistent. Let me write that here. So theorem, the two CH, the following theories are equiconsistent. So the following theories the are equiconsistent. So one is CH plus omega 1 then psi t on omega 1 and 2 ADR plus theta is regular, right? So this is the direction that I am doing. So 2 to 1 is 2 1 and 1 to 2 is out of myself, Trang, Wilson, and Zeeman. So the point is that before, so this problem was, I mean, this is a problem in Hughes in Wooden's big book to prove that these two theories are equiconsistent. But it was important for inner model theory because this was the test problem for Kolmar induction, meaning if we can prove that these two theories are equiconsistent by this method called the Kolmar induction. The method is called Kolmar induction because you were inductively building the Kolmar. Right, that's why it's called Kolmar induction. Okay, but in the early days of this, when the theory was being developed, it was unclear that you could do 1 to 2 without assuming the hypothesis here, without this assumption. So there was always this extra hypo here that the embedding restricted to the ordinals is the same as is independent of the generic, and yeah, so there was always that hypothesis. And then there was a recent advance in inner model theory, this full normalization technique, which Dominic, Naumann, I think Martin saw how to. So we established this. Myself, Trang, and Naumann, Trevor proved 1 to 2 imply using the hypothesis 1 here, and then the other, and then Dominic and Naumann, Martin saw how to get rid of this hypothesis. So I'm not sure if the hypothesis is interesting anymore, but that had historical reason for that. Okay. So we're in these lectures, we're doing 2 implies 1, right? Yes. Okay, so why do we, what is the method for getting this independence? It's the following. So let G equal omega R generic, H be add 1 omega 2 generic over Vg, right? Now suppose I is an ideal in VG, in VGH, and I is normal, let's say. I is on power set of omega 1 R and is normal. So what we want to say is that, okay, so we say I has ordinal covering with respect to V. This means ordinal covering, yes? If basically every ordinal that you want to represent in the I ultra power, you can already represent in the mu ultra power. So if for any f, so pick any function which would be representing an ordinal in the I ultra power, right? And for any I positive set, for any S in I, which is a positive set, that you can shrink it, that exists as prime I positive, right? So I can shrink it and find the function and f from p omega 1 f0 into ordinals such that, yeah, 1, okay, so we wanted S prime to be in V, f0 to be in V, and we want to f restricted to S prime is f0 restricted. So this would, we did things like this when we showed that you have some ideal and its generic ultra power agrees with the ultra power by measure 1, or by the solver measure. We did arguments like that, and it was always going through something like this. Okay, so but the main point of this, so the main idea of the whole proof is the following. Oh, let me remark why this definition is important. We need this property to get clause 1 here. Let's say this one, embedding independence or something. Right? So we need this property to get embedding independence. Okay. So the main new thing that we have to prove, in addition to what we already proved, is the following. So proof of the theorem, I guess. Right, so we fix H at 1 omega 2 VG generic. Right, so we're now going to look at the ideal that we already considered before. Now, I is the ideal. So let I be the ideal on R to the omega given by generated by A. So by A subset of R to the omega that are nowhere weakly omega. What does nowhere mean? So we had this notion weakly omega below P, i.e. for any P in the collapse forcing, A is not weakly omega below P. So if you remember what that meant, that means that for club of sigma that contain P, so weakly comega means below P means that there is a club of sigma and comega many generics that enumerate sigma, right? That belong to A. That's what it means. So this is our ideal. And now we force with the call omega r. So what is the idea? The idea is that we get omega 1 dense ideal on omega 1 if provided we can show that the generic embedding is induced by call omega 1 by collapsing omega 1. So if you collapse omega 1 to omega and that induces generic embedding, then you have it. Why? Because so what's the content of this statement? The content is that collapsing omega 1 to omega gives you the generic for the poset associated to the ideal. Now the key thing is that this forcing call omega 1, that's of size omega 1. So that means your forcing associated to the ideal is omega 1 dense, has an omega 1 dense subset. Because it's the generic is induced by this forcing of size omega 1. Okay, and then right. So, but now we have to just think of what is omega 1 and in our context, omega 1 is R. So in the above context, of situation in VG, omega 1 is the cardinality of R. So, so we want to show that the generic embedding is given by all omega R. So we will be collapsing R. Right? Okay, so this is the idea. Now we pick. So pick H, call omega R, a generic. And now we have to remember what we did earlier. I don't know if you remember. So we let UH be the set of all A in R to the omega such that there exists P in H and A is weakly comega below H, below P. We look at this thing, and what we showed that this is generating this is an ultrafilter. So UH is a ultrafilter on R to the omega, and if I do pi UH restricted to ordinals, this will be the same as pi mu restricted to ordinals. That's what we proved. This is what we proved before. Okay, so what we want to do now is look at the ultra power by this UH, right? So now consider pi UH, which is an ultra embedding from V into out V VUH, right? Okay, but now we want to lift this. So I'm going to call this J. Let's call this J, right? So now I want to lift this, but lift to what? We have to lift. So now, the next idea is, okay, we will lift to VGH. And how do you do usually this type of liftings? Well, let's see. So I think it's actually enough to just lift to VG because H doesn't H doesn't. So notice it is enough. It is enough to lift. As H does not add subsets of omega 1. What I mean by this is that because if I lift to VG, then and then derive the ultrafilter, that will be acting on VGH because it will be measuring all the subsets of VGH. Right, so I don't why I'm not sure if this is. I think it's okay. Yeah. Right, because it's enough to prove. Yeah, so the idea is that I will get that ideal, right? This is because so if we lift J to VG into algebra power of V UH G prime, then the ideal inducing J will be omega 1 dense. Because the forcing that induces this embedding is just the collapse. So it will be omega 1 dense ideal. But if it's omega 1 dense ideal, it will be precipitous in the after H. So I don't have to prove it will remain omega 1 dense ideal after forcing with H. H does not add new subsets of omega 1. Right? Okay. So this is the point. Now, if you have seen this kind of lifting arguments, what you usually do, so how do we do, because it's Arigit and Olaf, they probably haven't seen it, so just general remarks on lifting embeddings. So you have, suppose J is from M to N, and P is in M a poset, and G is M generic, and H is JP generic over N, and pointwise image of G is actually contained in H, right? So then there exists J plus from M G into N G prime, so GH, such that, okay, so you want J plus restricted to M to be the same as J, and 2, you want J plus G to be H. Okay, so how are we going to do it? Well, it's not hard at all. Just set J plus tau G to be tau H. sorry, J tau H. So the point is that my J is acting on tau because tau is just a name, right? So I pick a name, I send it by J, and I evaluate by H. So why do I need this condition? This is the thing to understand. Why do I need this condition? Well, to prove that the J plus is elementary. To show J plus is elementary, we need that G is subset of H. Well, so how does it come up? Here. Suppose Mg satisfies P tau 1. Let me put G here to make it easier. And let's say tau n G, right? So then what? Then there is a condition that forces this thing. So from here you get, there is a condition in G by forcing theorem such that M satisfies that P forces phi tau 1 blah 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 tau n. Okay, but now I know that if I take P in G, then its image is going to be in H because of this condition, yeah? So I have, this means that J of P, so there exists Q in H, namely JP, such that N things, now J, this is Q forces P, J tau 1, blah, 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 J tau N. And so that means what? That by forcing theorem, that means that NH satisfies P, J tau 1 H, J tau N H. That's exactly what we want. We want, this proves elementality, yeah. All right. So let's go back to the situation we are in. If I want to lift this embedding, what I need to do is find G prime such that it contains pointwise image of G. And once we do that, then there is nothing really else to do. So let me just tell you how we do it, and I guess it's a short meeting. Just tell you how we do it. Right. So we now build G prime such that JG, right? J pointwise image G is contained in G prime. What property are we going to use for this? The property we're going to use is the countable closure. So the way these arguments usually work, no matter where you do in with large kernels or without large kernels, you usually count. Usually your poset has to be closed enough, and you're supposed to have not too many dense sets. So then you just meet these dense sets one by one. So here's what we do. First, notice here is first remark. First important remark. In V, collapse omega 1 R is isomorphic to, sorry, collapse omega R is isomorphic to what, to collapse omega 1 R followed by some poset Q. That's because collapsing reals to be omega, it's universal. So what I can do is I can assume this means we can assume that H is VGH generic, right? Remember, H is the one that collapses the reals to be counted. And the next thing is that G is in VH. So how would you do it? Well, this is the part that's tricky, yeah? B. So I know that because H is, if you put G here, right, and call omega 1 of R, you put G here, there is some other generic that gives you H. This is because H is G. I mean, I have to change the G, and what I mean is that when I said we can assume is that we can pick G and H. So i.e. we can pick G, H, H such that, right? So what we need to do is we need to write H equals G star some H prime because of the factor, this factorization, right? So you know your G, there's always some H prime that gives you this H. And now pick the H generic with that property. So you can always pick this kind of configuration. Right. So now we work. So we want to find. Okay. So we will find the prime in VH. So J lifts to V VG out VUH G prime in VH. G doesn't play a role anymore because I'm assuming G is in VH. That's why there is no need to mention it. Okay, so we do, and so how are we going to do it? Well, so we have, right, so we are counting, we need to count how many dense sets, subsets, dense subsets J P has in P being the collapse function, the collapse forcing, right? P is the collapse forcing, has in the ultra power of V UH. We need to count in VH, right? The counting has to happen in VH. We need to count the number of 10 subsets of JP. So let me make the sentence more proper. So working in VH, right? We count the number of dense subsets of JP that are in the ultra power by this. Okay, so at JP, so here are the steps. So one, notice P, which is called omega 1 R, is coded by a set coded by a set of reals. So 2, every then subset of P is a set of reals. Because P is a set of reals, subsets of P are also a set of reals, right? Now 3, every dense subset of JP in the ultra power is a set of reals in the ultra power. So we need to count how many dense subsets, how many sets of reals there are in the ultra power. So we need to compute the cardinality of our set of reals of the ultra power VH, VUH, in VH. Right? That's what we need to do because every dense subset of JP is a set of reals. So we need to count how many set of reals there are in the ultra power of V by UH. And we are doing this counting inside VH. Okay, every such, so 5, every A, which is a subset of R in ultra power of VUH, is represented by some F from R to the omega into our set of reals in V, right? So it can be coded as set of reals. Such F can be coded in V by a set of reals. How? Well, so what do you do? F is equivalent to xy to the set of xy in R2 such that y is in F. I'm thinking of x as giving me omega many reals. So x0 xn, where x0 xn is in our omega is coded by x. So you fix some coding of one real into, so you can look at the prime coordinates. I give you a sequence of integers, right? That's what the real is. You can just look at the prime coordinates. So your nth real that x codes are the ones that take the nth prime and look at the powers of this prime and look at the digits that sit on exactly those places. So you can cook up many different ways of getting omega many reals out of one real, fix one, and use that coding to do this. And this is obviously can be coded as a subset of R, right? Okay, so what did we show? Every set of reals in the ultra power is coded by a set of reals in V. That means the cardinality of set of reals in the ultra power is the same as the cardinality of set of reals in V. So in VH, the cardinality of the power set of reals of ultra power of VUH is the same as cardinality of the power set of reals of V, right? By the way, when I write this, it doesn't mean it's the same reals, right? Alt VUH has more reals. So what I mean is you take the reals of alt VUH, you compute all of its subsets, and that is the same as the one in V. Okay, but how many are these? 7 in VH. The cardinality of power set of RV is omega 1 because cardinality of R is omega 1 in V, and which implies, and 2 to the omega, and 2 to the omega is omega 1 is omega 2, right? Because theta, and theta is omega 2 basically. This is why. Okay, but this is not enough. Why is this good news? Here is why this is good news. So fix f from omega 1 into dense subsets of omega 1 of VH, which is omega 2 of V, which is theta of, sorry, it's omega 2 of VG and it's theta of V. So dense subsets of JP in the ultra power of V by UH. So we fix the bijection F F a bijection. Now, another thing that we need to notice is that, so this is the second important observation, that the reals of VH and the reals of the ultra power are the same. Ultra power, yes, ultra power V by UH are the same. This is, I mean, this is the general ultra power fact that I think we did this before. I either did this or it is easy. What do I mean by, well, you just have to show that, maybe it's not that easy. Just need to show that everything is represented by a function, right? So for example, what would represent H? H itself is a real. It would represent the function that, right? So for example, maybe I will do this after I finish the proof. So let me put here that we will show this later. We will show this later. Okay. So this is the second important thing. And why is this important? Well, it's important because notice, so because G is in VH, G is coded as a real in VH, right? What is G? G is essentially a function from omega 1 of V into R, but we are collapsing this, so it's coded as a real. We have J G is in the ultra power. Because it's just a real. It's even the same point, right? Notice JG is just G because J restricted to R is just R. RV is just R. Reals don't move when you apply elementary embeddings. Okay, so what we do is we build use F. So Okay, so we have omega 1 many dense sets, right? There's omega 1 in VH, we have omega 1 many dense sets. We have this condition. So all we now want is the third important observation. Third important, which follows from here, I guess. Important observation. This is that VH thinks JP, which by the way is J collapse omega 1 JR, which by the way is equal to collapse because of the equality here. It will be collapse omega 1. This is omega 1 V. This will be 2 omega 1, omega 1 VH R. This is RV, right? Sorry. This is J col omega 1 V RV, which is equal to col omega 1 of VH. I wrote VH satisfied, so this is okay, R. And R is VH. That follows from the second important observation. So VH thinks that JP is omega closed. Omega 1 closed. Right? Okay, so we have omega 1 many dense sets and of an omega 1 closed poset, which means we can get a generic. So working in BH, we have 1, JP is omega 1 closed, and 2, omega 1 dense subsets of omega 1 dense subsets of JP. So we can get a generic. Oh, let's see. So I'm not doing anything wrong, right? JP is omega 1 closed in VH, not just in the ultra power, but in VH, because it's this forcing. Yeah. In general, you couldn't do this because I think in our paper we take P, which is just an arbitrary omega closed poset, and then this wouldn't work. But for this particular P, I actually have that it is omega 1 closed in VH. So if you take P to be an arbitrary omega closed poset, then you have to work a little bit harder. But for this particular P, it is actually omega 1 closed in VH. And so we can really just get we have JP's omega 1 closed, omega 1 subset. So we get H, which is, oh, sorry, G prime. That is ultra power of VUH generic over, sorry, that is generic over the ultra power, and it contains this particular point, and G is a subset of G prime. So just start with G. G is a condition, right? It's countable. In the algebra, it's countable. So start with G and hit every dense set, and you have omega 1 many. At each stage you have countable set of countable chain, right? Count the set of conditions that forms a chain, so take an upper bound and continue meeting your tensors. So just like when you prove that if you have omega many tensors, you can find the generic for those omega many. Okay, so that's it. Then we have what? So now we have J lifts to J plus from VG into out V U H G prime in VH. Okay, so finally, what is my ideal that's going to be dense? So now we consider the following ideal. On P omega 1 of R of V G. Which, by the way, we have, because we didn't add any new countable sequences, G was omega closed. We have that this is the same as this. Okay, so what is the ideal? Well, set A in, so given, right, so given A subset P omega 1 R, let A, yeah, so of V, yeah, let A in I, this is the standard thing that we are doing now, if and only if the empty condition, so it's forced by the collapse, so it's forced by the collapse forcing, this is the collapse forcing of V, that the reals of V, this is the reals of V, that does not belong to A, J plus A. Now J plus is this lift up that I get, right? So I'm fixing some kind of name for it. And Mhm. Okay. And then, okay, so we now have, so we have I is because P, the generic for I. So I mean, this part is kind of standard stuff. So because the generic for the forcing gravity I is added by for omega 1 R, we have that I is dense, omega 1 dense in VG. Moreover, I is normal, fine. So we actually have, so these are easy to prove. It is easy to prove. I is fine, normal. So why is I normal, for example? It is normality. So what does it mean to be normal? It means that suppose I have S, X, X in R, subset of I, want to see that the diagonal union, right? So the set of sigma in P omega 1 R such that there exists an X in sigma is in Sx. We want to see that. Okay, so let me rewrite that. So we want to see that the set of sigma in P omega 1 of R such that there exists an X in sigma with the property that sigma is in Sx, right? This is in the ideal. Okay, so what does it mean to be in the ideal? It means that it's never the case that R is forced to be in the J image, i.e., want to see that it's forced by the collapse omega R, that R is never in J image of this, in J plus of this. But what is J plus of this? Let me call this set B. Yeah, is in J plus of B. Okay, so let's assume that opposite, meaning collapse omega R does not force this. So suppose not. Okay, if you assume not, then there will have to be a condition in call omega R such that P forces that R is in J plus B. But what does it mean to be in J plus B? It means, so this means that P forces that there exists an X in, right? So let J plus this vector, this be, let's say T, X is in J plus of R. That means there exists X in R such that R is in Tx. That's what it means. But let's see, if I pick an X in R check are the reals in V. That means Tx must be J of S of X. So this means P forces that there exists X in R hot such that R is in J of S of X. I shouldn't be actually saying it like that. This is actually not true. Right? So we pick P forces this, but that means I can extend P to some Q. So there exists a Q and X in R such that Q forces R hat is in Tx. And now I can say, so this means that Q actually forces that R hat is in J plus of Sx. But this means that J plus Sx is not in the ideal. I mean, Sx is not in the ideal. This means Sx is not in the ideal. Because we put something in the ideal if every condition was forcing that it's not in the J plus, that R is not in J plus. But here we found the condition that forces it is. Okay. So this is the proof, really. We now have everything we want. So I didn't prove that. So we can moreover prove that this ideal I is has the covering property with respect to VG, V. Okay, so how you do that? Okay, so here's the proof. Let f be a function from S into the ordinals, and S be in I positive, right? And F is in BG. Now suppose, so it S is in positive. So I'm taking, so because S is I positive, that means some condition forces, right? That it's not in the idea, it's not, that this R is not in J of it. So there exists P in collapse omega R, such that P forces, the reals must be in S, J of S, J plus. Otherwise, if no condition forces it, then it's bad. Then it will be in the ideal, not in the positive set. Okay, so we have this condition which forces that R is in the J plus S. Okay, so we look at the value of this particular function. I mean, so now we have a oh, I can further extend P, so we can further or so I can further extend P and find, and there exists alpha such that Q forces Fr is equal to some alpha, right? So I can further extend P to decide the value of F at R check, sorry, J plus F, so the image. But now I can pick a function in V, so now let F in V, F0 in V, be such that its value is alpha. Okay. Now we have what? So but F0 is the function from P omega 1 of R into ordinals. So now I have that the, now notice, this is the key point, that F0 mu, this is the what we have already proven when we did these calculations. This is just that, which J plus, I've been calling this J plus. So by J plus, I mean the name for the embedding, right? Basically, what do I want to prove? Let's just write what I want to prove, then it will be easier. So we want to show that the set of sigma in S such that F0 sigma such that F sigma equals F0 sigma is I positive. By the way, I think I made a mistake in the definition of ordinal covering. I don't, only F0 should be in V. S prime does not have to be like this. So we want to show that the places where these two functions agree is I positive. So what do we do? Okay, I positive means that no condition forces, so some condition forces that reals will get in there, right? This is because Q forces exactly that. Let's call this set C, that R check is in J plus C. Because we know that if I apply the reals here, I get alpha, and if I apply reals here, I get alpha. So this is the reason. So some condition forces reals end up in that image of that set. That means the set is I positive. Okay, so I owe you one more thing, namely why the reals are the same, right? This equality. So let's do that too. The last name, the reals of VH are the same as the reals of the object power of V by UH. And okay, so we need to represent every real in the algebra power, right? So proof that how the collapse omega R name for a real. How is essentially what? A set of reals is coded by a set of reals. So we think of it as set of reals. Okay. But so before I do that, I need to show that H is in. So first step, H is in the algebra power of V by UH, right? Now, what function would represent this H? So consider set A, which consists of X in R omega, such that X is X. So I want to look at those X's such that for, yeah, so there is a club of yeah, just look at the identity function. I don't know why it's, yeah, let's just look at the identity function. Just f be the identity function on R, right? Then what is identity function? Relative to UH. Then we claim this is the same as H, right? So what is it that we want to show? We want to see that the identity function UH n is equal to Hn for every n, right? So this means what? By Cauchy's theorem, what exactly are we trying to prove? Hn is a real in V, yeah? So we want to prove that the set look at the set of sigma. No. It's weekly comega, yeah. Oh, UH was, you have to go to UH. So UH is, A is weekly comega below P. What does it mean to be weekly comega? That means for comega many, for a club of sigma, comega many enumerations are in A, right? So let, I guess, let P be the condition to be H up to n plus 1. This is my condition. And now I look at the set and consider the set A, which consists of reals in, omega sequences such that for a club of no. This is so this is the set of X. No. So for club of sigma, yeah. Oh, so notice this, yeah. So we have for co-omega for club of sigma for club of sigma. In fact, for any sigma containing P, right? For any sigma that has P as an element, for any X which enumerates sigma with X below P, right? So with X up to n plus 1 equals P. Xn is equal to Pn. So for any sigma, for any X which enumerates it, Xn equals Pn. So the set of A, so the set A, which is just r to the omega such that Xn equals Pn, is weakly omega below P. Sorry, the set of X such that Xn equals Pn is weakly omega below P. But what does this mean? This means that A is in UH, which means what? Which means that the identity function is going to give us Hn. So this means that identity UHN is equal to Pn, which is actually Hn. So it's the identity function that's going to give us H. Okay, but then if you soup up the same thing, so now by basically the same proof, right? By repeating the same proof, essentially the same proof, we get F such that F Okay, so how would you do that? Well, you want to look at tau, it's a name, right? So consider uh, that, do I have time by the way? Oh, so I have a little bit. So let m tau be m tau sigma be L, for example, L tau intersection sigma sigma, right? Okay, so I can look at an enumeration, generic enumeration of sigma and evaluate the value there, right? So for m tau sigma generic x, let f of x be the evaluation of tau intersection sigma evaluated at x. It's just some name of a real, right? So this is a real inside L inside m tau sigma adjoin x. Okay, and that's what you want to do now. So we want so we can show it then follows that f mu h is actually going to be equal to tau h. Because, right, if I look at what would f represent? You have to go look at the soup, right? So the function sigmas represent reals, right? This is because x goes to range of x represents R, right? So if I look at what each countable sequence the set that it enumerates, that's going to represent my V reals. So what is f going to evaluate? It's going to ask you, you have now your sigma is this real, tau and x goes to tau intersection sigma, tau intersection range sigma represents tau. And so we have, and we have the identity represents, right? And x goes to x. So you get this equality. Basically. All right. So that was very smooth because Lukasz was not here. Okay. Let me stop recording.